I've got to move this out of here if I'm going to have a better chance of taking off. Oh, great. How am I supposed to move it now? No matter which way I push it or pull it, it won't budge. Just about lift it. But how's that going to help? I need to think about this after I answer the science line. What's going on out there?
Stella, we're a bit stuck on something.
Yeah, we're all on this wooden floor, but some of us can slide around and some can't.
It's because my trainers have got rubber soles. They're stickier than your leather ones.
I reckon it's got something to do with forces and weights.
No, we all weigh about the same. I can slide around easily. You can't even get started.
Why is that, Stella?
OK, leave it with me. We're not dealing with sticky things here. We're dealing with forces. Look at this block. If I push it along here, I'm exerting a force on it and it moves. But if I also push from the other side with an equal force, it doesn't move. The forces are balanced. If the forces acting against an object are balanced, then there's no movement. So, if you're wearing trainers and really trying to push your foot along the ground and failing, it must be because there's an equal force acting against the foot in the other direction. And this force is called friction. So, friction is the force that opposes movement when two surfaces try to slide over each other. And one of the things that the size of that frictional force depends on is what the surfaces are made of. Now, it looks like I might have my own friction problem here, but I need to know more. I think it's time Femi investigated.
Now, if there's one thing I know about forces, it's this. If I'm not moving to either side, it's because one of two things. Either there are no forces pushing against me, like now,
Or there are equal forces, like this.
It's only if the forces aren't equal that you get movement. But what I want to investigate is how, when something's being pushed one way, it can have an invisible opposite force of its own, and that force can get bigger. This is a scrum machine. It's what rugby players use to practice their scrums on. Now, by itself, it's easy enough to push, right, Sarah? Yeah. What happens if you put some weight on it?
How about us?
How much do you two weigh?
About 200 kilos?
I think they do. Let's take a look at this. At the moment, the machine is stationary, as there are no forces pushing on either side. Now watch. OK, Sarah? Sarah is pushing with the force of around 300 newtons. But the machine is still stationary. There must be something stopping it moving. A force pushing back against Sarah. It's friction. Friction is a force that's created by these two surfaces rubbing against each other. Now, as the machine isn't moving, we know two things about it. One, it's acting in the opposite direction of the push, and two, it's the same strength as the push. What's going on? Well, on a microscopic level, it's like this. Now, the bottom of the sledge machine may look smooth, but through a microscope, it's uneven, and so is the grass. Now, let's say These studs represent the microscopic view of the uneven surface. Now, when there's no weight on them, they move across the top relatively easily. When there is weight on them, the two uneven surfaces lock and they're harder to move. Now, the machine is gripping the grass just like Sarah's boot. Oh, I forgot to tell them to stop. Sarah, I'm so sorry. Don't worry. I'm going to get you some help. Let's see what happens when we increase the pushing force. Another pusher means the force is now around 600 newtons. Still no movement, so the frictional force must be around 600 newtons too. It's got bigger. With 3 pushers, the force increases to 900 newtons. And so does the frictional force. In fact, it grows at the same rate as pushing force until the force pushing the machine is greater than the frictional force. Well done, team. Oh, I forgot to tell them to stop again. Oops. I'm sorry. I'm very sorry. I'm going to go home.
Oh, we'll give you a lift, Femi.
Ah. Never really liked rugby, but I could be converted.
Oh, so friction will oppose me no matter which way I push this. And because of the way the surface of the bottom of the crate and the surface of the floor interact, I'm not going to be able to generate a force by myself larger than the force acting against me. So what can I do to move this?
She should get down the gym and do some weight training.
Yeah, then she'd be able to push with a force greater than the frictional force.
No, that box is far too heavy. She'd need a forklift truck or a load of people to help her.
Maybe it would help if the bottom of the crate wasn't so rough.
Yeah, or if the surface of the floor was smoother.
I could just lift the crate. So if I could get something smoother underneath it, that would make the friction less and I wouldn't have to use so much force to move it. But what sort of thing can I put under it? I know what might help. This is my sledge. Meant to slide, isn't it? But what about this rubber on the runners? Could be a problem. We'll see. To move this, I need to apply a force of 220 newtons. Can my sledge improve on that? Oh, this made things worse. 320 newtons. The rubber on the floor has increased the frictional force. I'm going to have to try some different materials on my sledge runners. I've organised an experiment to find out which material has the least friction force when it moves over the aircraft floor. I'll use this block to represent the sledge runner, weights to represent the crate, and this is the floor. Now first, I'll attach in turn each of these materials. And then I'll attach a forceometer onto the block and try and pull it across the flooring. And the forceometer will tell me how much force is needed to be greater than the friction force. Polythene. Shiny. Sandpaper. It's a bit rough. But then put sand under the block. Might work. Baking tray. This is non-stick Teflon. All in the cause of science. So some obviously did better than others. Sandpaper, made up of all those tiny grains, 68 newtons. Wood, 42. Polythene, even though it was very shiny, still needed 36 newtons. But the material with the least frictional force of those I tried was Teflon, 30 newtons. So, all I have to do is put Teflon on my sledge runners, and away I go. Have I got any more baking trays? While I'm looking, I think Femi should investigate a place where other people make good use of rubber and Teflon in their battle with friction.
Before I do my investigation, I'm wondering why I have to wear these strange shoes. One grips, and the other slips. The grippy rubber shoe enables me to slide on the slippy Teflon shoe. Actually, I think I know now. Kirsty Hay is a champion curler. The main idea is to try and land the stone in the middle of the target. Hiya, Kirsty.
Hi.
Now, I'm here to investigate how friction can help and hinder you.
Well, you've seen the shoes, and to grip and to push off, I need the high-friction rubber shoe, but to slide and to deliver the stone, I need the low-friction Teflon shoe.
Anything else? Because obviously the ice is slippery, so that must be good.
Well, actually, it's not slippery enough, and we have to pebble it. Paul? Pebbling is when we put water drops onto the ice. It instantly freezes and you get a bobbly surface.
But surely pebbling makes the ice rougher, not smoother. In fact, it feels rough. Isn't that just going to slow the stone down?
I'll bet you that's faster.
OK.
Kirsty is throwing two stones with exactly the same force. The blue stone on the right is on flat ice, the yellow one is on pebbled. The yellow stone soon gets ahead. What's going on? On smooth ice, two flat surfaces rub together. More contact, more friction. On pebbled ice, the stone only touches the ice on top of the peaks. Less contact, less friction, more speed. The winner!
That's more like it. Does friction only exist between solids? These two balls of plasticine are the same weight. If I drop this ball into water, it sinks. But what happens if I drop this ball into this jar?
In the tank on the right is silicone oil, a thicker liquid than water. Silicone oil offers more friction to the sinking ball than water, so the ball sinks more slowly.
Changing the liquid isn't the only way to change the frictional force in a liquid. These different shapes are the same weight. If I drop these shapes into silicone oil at the same time, we'll see if the shape makes any difference to the force of friction.
The shape does seem to make a difference. The teardrop seems to be experiencing less friction than the other shapes. Something for Femi to investigate.
Cycling. You can't beat it. But I'm off to see someone who can make me go faster without me doing any training.
So, Joss, how can you make me go faster?
Well, when you cycle, you can feel the wind on your face. That's the force of the air pushing against you. So if we can reduce the force of the air, you'll go faster.
Excellent. Thank you.
I'm in a wind tunnel, so rather than me pushing through the air is going to be pushing past me. Joss Darling is an expert in how air flows against solid objects. It's called aerodynamics. The giant fan is set to make the air travel at 25 miles an hour, the equivalent of a windy day.
air forces me backwards. The force is called air resistance or drag. This apparatus measures the drag. It is linked to Joss's computer, which shows the force against me is 45 newtons.
Joss, so what's actually happening when I'm on the bike?
Well, the wind that you feel is actually particles in the air hitting you. It's a bit like this. And because there are lots of particles, the force that you feel is actually quite strong. And you can see here that the air's coming along and it's walloping the front. It's having to change direction, go over the surface. The result of that is that at the end of the day, there's a force trying to stop you moving. And that's what you're feeling when you're pedalling on your bike.
The particles are like the surface of the air rubbing against me. When I'm sitting upright, more of them push against me, which slows me down. Bending down means fewer particles need to change direction, so the drag is less, 25 newtons, but Joss still isn't happy.
There's still quite a lot of friction, Femi, and a lot of it's in your clothes. And this model is meant to represent the surface of your clothes flapping in the wind. And you can see that as the air comes along, the bubbles get caught in the hollows.
They change direction, so exert a force. You can see it on my flapping clothes.
And also, the surface of your clothes are quite rough.
Well, yes, actually, if I slide my hand over the cotton, I can feel that friction, and that must be what happens in the air as well.
That's right. So if you had something that was much smoother and the air could slide over more easily, there'd be less friction, and hopefully you'd go more quickly.
So, smooth, tight clothing is called for.
I need to get changed. Don't look! Meet the new aerodynamic low-friction Femi. Go for it, Joss.
This is much better. Look at that airflow. The teardrop helmet helps smooth things along. 17 newtons, just over a third of the drag I started with. Time for a road test. Don't worry, Joss, I'll be back before you know it.
Now I know how to reduce the friction force. Moving these is a lot easier. Before I go, here's something for you to think about. When I move this crate out onto the ramp outside the plane, it will slide down without me having to push it at all. Now, the ramp is made of the same surface as the floor, and the crate made of the same wood. So why do you think that is?
Obviously, the ramp is slippier.
No, she said it was the same material as the floor.
I reckon she gave it an extra hard push to get it going.
It's sloping, isn't it? Be helping to pull it down.